Hello, everyone. Welcome to the second lecture of the lecture series on elliptic curves with complex multiplication. Today, we will discuss elliptic curves defined over the complex numbers, and in particular, elliptic curves with complex multiplication defined over the complex numbers. So recall last time we defined elliptic curves. Elliptic curves is a smooth projective algebraic curve of genus 1. Curve of genus 1 with a marked point. So we usually denote the curve as E and the marked point as O, which would usually be a rational point of E, okay, whichever field E is defined over. And moreover, we discussed that the set of points on E, whichever field, actually take any field extension L over K. We know that the set of L points on E forms a group, forms an abelian group. And this group structure is algebraic. So the group homomorphisms are actually algebraic morphisms of algebraic varieties. So this is actually the reason why last time when we defined the group law on the curves, we use the identification of the points on the curves with points in its divisor class group. So if you read some books on the curves, very often they define the group law by intersecting the elliptic curve with a line, and then tell you that, well, elliptic curve is defined by a cubic equation, and it will intersect at 3 points, and using these 3 points relationship to define a group law on set of elliptic curves. You can define that way. But when you define the group law that way, it's less obvious to see that this group law, for example, will always be defined over the ground field, and also it's less obvious to see that when you have isogenies, you always have dual isogenies. So in order to explain all this more complicated structure, I identified the set of geometric points on the curve with the with the divisor class group. Okay, so that's what we discussed last time. But as you can see, this definition is actually very, very abstract, right? Well, I did give you a defining equation. I did tell you that the curve, you can very explicitly think it as a vanishing locus of a Weierstrass equation that looks like y squared equals x cubed plus ax plus b, as long as your characteristic of k is not 2 or 3. This is one somewhat concrete description, but it's still sometimes hard to visualize points on elliptic curves. So today we will make things more concrete by starting elliptic curves over C. And moreover, last time, the very important thing we discussed last time is the concept of CM elliptic curves, which is the topic of our whole lecture series. So CM elliptic curves. So by definition, we said CM elliptic curves are, so let's first assume that my characteristic, my base field is 0. Then I call elliptic curve having CM when the geometric endomorphism ring, algebra, I guess ring, is isomorphic to a so-called order O, which is an order of some imaginary quadratic field, Q adjoint square root minus D, right? So I just told you that such elliptic curves exist, right? But then I did not tell you how to construct such elliptic curves, how many such elliptic curves are there, and how to start it, right? So today, what we're going to do is we're going to work over C. So today we're going to take my field K equals to C, and we're going to study elliptic curves over C. And moreover, CM elliptic curves over C. So today we are going to give you a way to essentially think about how to construct elliptic curves over C, how to even eventually parameterize all elliptic curves over complex numbers, and also how to explicitly construct CM elliptic curves. And also this will also tell you, like, given fixed order of an imaginary quadratic field, how many CM elliptic curves are there whose endomorphism ring is exactly isomorphic with order, for example. Okay, so that's the topic today. So let's start. So start with the first topic, elliptic curves over C. So elliptic curve is a genus one. So let's think about, so E is a genus one algebraic curve. A genus one curve. So which means that topologically, if I consider EC, the set of C points on my elliptic curve, then topologically, it's a torus. Topologically, it is a genus one Riemann surface. So genus one Riemann surface, which we can also just think it as, it's literally just a torus topologically, right? So it's a torus T. And well, how do we construct a torus? If you remember, so in topology, we construct a torus by essentially having a rectangle and identify the corresponding two sides, right? So this is a torus. And another way to think about it is think about the universal covering. Universal covering of a torus is actually R2. And then I model out a back transformation group, which is two copies of Z. So you can essentially, we want to identify all of these sides. So inside the R2, right? So the point is, inside R2, I take any point xy, and I identify an equivalence relationship, which is xy identified with x plus m, y plus n, where m, n are in Z. This gives me a torus, right? And so this tells us that essentially we can construct elliptic curve, a complex elliptic curve, the same way. Namely, let's talk about. So the point is, let me first make a definition. Is a lattice lambda inside the complex number C is a discrete subgroup of C which contains R basis for C. Okay. So moreover, this is a question that I'm leaving it to you, which is such a lambda is actually always a rank 2 free Z module. So such a lambda is always, you can always concretely write it as n1 times omega 1 plus n2 times omega 2 for some n1, n2 in Z, and omega 1, omega 2 are complex numbers in C that are linearly independent. Okay, so such a subgroup of C is called a lattice. And very concretely, if I think about C as think about my complex plane, this is my real axis, and this is my totally imaginary axis. Then a lattice is exactly, if I draw the set of points, lattice points, it will exactly, if I connect the lattice points, I will exactly get get a discrete subgroup isomorphic to Z2 inside my complex plane. So which means that if I'm not drawing a great picture here. There is a way nicer picture. Oh, did I draw a nicer picture in notes? I draw a picture in the notes. So let's see if this is my omega-1 and this is my omega-2, for example, right? So then they will form omega-1, omega-2 will form a parallelogram, and moreover, as you can see that this is my complex plane C, right? So this tells me that C mod out this discrete. This is my lambda is the discrete subgroup with containing the points, these lattice points. Okay, these are the lambda points inside lambda. So you can see that C mod lambda is topologically exactly a genus one Riemann surface. Right? Is a genus one Riemann surface. Is a torus. Let me just write a torus. Okay. And moreover, with the addition of C mod lambda is actually a complex Lie group. Okay. So I can think about this object C mod lambda. And if I have two lattices, okay, given two lattices, lambda 1, lambda 2, I can consider maps between them. So maps between C mod lambdas. So maps C mod lambda 1 map to C mod lambda 2 as complex Lie group are exactly identified as, so these are in bijection. So maps, this set is identified as complex numbers alpha in C such that alpha Z alpha times lambda 1 is inside lambda 2. So the point is, any map C mod lambda 1 to C mod lambda 2 descends from a map C to C. So phi of alpha is C to C by mapping every element Z to alpha times Z. This is literally defined by multiplication by a complex number. And then for this map to descend to maps between these quotients, we will need alpha times any point in lambda 1 to be in lambda 2. So that is a well-defined map on the quotient group. Great. So then this gives us essentially a category, namely, so this gives us a category where objects are lattices, lambda in C. These are lattices. And on the set of lattices, I can define a equivalence condition, which is called homosety. Homosety means two lattices are homothetic means that there exists alpha such that lambda 1 literally equals to lambda 2 for some alpha. Okay, this is called homothetic. Okay, so I can think about the set of lattices in C after homosety and where the morphisms are exactly these maps that are phi alphas. So alpha in C. And then we consider the phi alphas that are C mod lambda 1 to C mod lambda 2. Okay, so such that alpha lambda 1 is inside lambda 2. Okay, these are the morphisms. So the first goal of today is we want to show essentially equivalence of category to the category of elliptic curves over C. So to elliptic curves over C up to isomorphism. And the morphisms are exactly isogenies that we talked about last time. These isogenies are nothing but morphisms between two elliptic curves, which are both which both is algebraic, so respects its algebraic curve perspective, and also group homomorphisms. Okay, so we're going to show that essentially there's an equivalence of category between the set of lattices up to homocity and isomorphism classes with the curves defined over the complex numbers. Okay, so let's do this by the first step. Okay, so this is the goal, the first goal, at least goal 1 of today. Okay, so we're going to do this by first going in this direction. Okay, so we're going to first try to associate associate to every lattice lambda an elliptic curve E. Okay, so we will associate each lattice lambda inside my complex plane C an elliptic curve. Elliptic curve E lambda. Okay, so in particular, what we want to do is I'm going to define a map from C mod lambda to the set of C points on this elliptic curve. In particular, we want to define such a map. So we want to define a map from C mod lambda. So any point that is so think it as, so if you think about C mod lambda, right? I can take one of these squares. So this is my, let's say that my lambda is given by omega 1z plus omega 2z, for example. This is my omega 1, this is my omega 2, right? And then C mod lambda essentially are the points on this parallelogram, right? I want to associate each point on this parallelogram a point that is on the that to associate a complex point of some elliptic curve. So this is our goal. Okay. So to do this, we need to first define some functions. Define functions on C mod lambda. Okay. So we want to define some functions on the points of these parallelograms, right? Because if you think about how do you represent, okay, so think about if my elliptic curve is given by a Weierstrass equation, x squared equals to x, y squared equals to x cubed plus ax plus b, how do I identify a point? I identify its coordinate x comma y, right? Then what are these coordinates? These are functions. These are functions on elliptic curve, right? On EC, right? So the point is, if I take EC and map it to x, take its x coordinate, this is a function on it, right? So then if I want to identify a point on my elliptic curve with a point on these lattices, I need to have functions on this quotient of C by my lattice, right? Okay, great. So let's define some functions. So we're going to define the following function, which is called the Weierstrass P function. Weierstrass P function. Okay, so its definition looks a little bit complicated, but that's fine. In the end of the day, it's just a function. Okay, so a Weierstrass P function is defined as follows. So P of z is defined as 1 over z squared plus a summation over, so you can only define a Weierstrass P function associated to a lattice. So you already have the data of a lattice, okay? So then P of z is defined as 1 over z squared, and then a summation over all the lattice points. So omega in the lattice you already have. That's a non-zero of 1 over z minus omega squared, then minus 1 over omega squared. Okay, so this is a Weierstrass P function associated to a lattice lambda in C. It looks complicated, I admit it looks complicated, but what's important is it satisfies some nice properties. So first of all, so properties. So what does it satisfy? So first of all, it's meromorphic. So it is meromorphic. Okay. Meromorphic function on C with double pole with double poles on lattice points. So it has a double pole. For example, you can see it has a double pole at 0, right? It has a double pole on every lattice point. But apart from the lattice points, it converges absolutely and uniformly on. So it converges absolutely. So series, this dimension converge absolutely and uniformly. So it is well defined on every other point. On every compact subset of C mod lambda. Okay, so it's well defined. Okay, and the most important thing is the following. The most important thing is that it is invariant under translation by a lattice point. So P of Z. So 2 is really not appropriate. 2 is just saying that it's well defined in some sense. Okay, so the series converges. Okay, so it's just saying that function is well defined, essentially. Okay, really, there are two properties. One of them is it is meromorphic on C with double poles on lattice points. And the second thing is that it is invariant under translation by a lattice element. So P of Z plus omega equals to P of Z for any omega inside my lattice. So this tells me that so for any and also any Z. So this tells me that P is a function on C mod lattice because it does not change by translating by lambda, right? So this tells me that P is actually descends to a function on my quotient, which is what I'm looking for. So I want a function that is well defined on my parallelogram, and even when my parallelogram gets translated by any element in my lattice. Okay, great. And such functions, actually functions satisfying 1 and 2, are called elliptic functions. So functions satisfying 1 and 2 are called elliptic functions. So these are exactly the kind of functions we're looking for. These are the functions that are defined on the quotient C by a lattice. Okay, so and P, the Wells P function, is one example of an elliptic function. Okay, so why is P particularly important? Well, if I look at all the, so all elliptic functions, so given, let's see, so given a lattice, given a fixed lattice, all elliptic functions with respect to this lattice, all elliptic functions form a field, which we can simply denote by C of lambda. They form a function field, okay? And then the important thing about this Wells P function is that this field C joint lambda is actually, this field is generated by the Wells P function and its derivative, the first order derivative. Okay? So Wells P function and its first order derivative generates the function field, means that every elliptic function is a rational combination of pz and p squared, p prime z. Okay, great. So now we are ready to associate. So now we're ready. Now we are ready to to construct an elliptic curve E lambda from a lattice lambda, right? Such as C mod lambda can be identified to the set of C points of this E lambda. Okay. Well, so the point is a point on any elliptic curve need to satisfy a Weierstrass equation, right? So if Weierstrass equation, so it needs to satisfy something like y squared equals to x cubed plus ax plus b for some ab. Okay. So what we are going to do is for each point, so for each point z inside C mod lambda, we are going to consider its value p of z and p prime of z. Okay, and we will show that these two values does satisfy an equation of the Weierstrass form. Namely, we will show that p prime of z squared equals to 4 times p of z cubed plus a p of z plus b for some very explicit a and b. Okay, this is what we will show. Okay, so but once we have this, you will see that this equation defines a elliptic curve, and I give you a map. The point, so once we have this, so this Weierstrass equation defines an elliptic curve, and more. So so we will define E lambda as the elliptic curve defined by y squared equals to 4x cubed plus ax plus b. So this is an elliptic curve. And moreover, I have my promised map, C mod lambda to E lambda C points by very concretely mapping each point z to p prime z. To p of z comma p prime z. Okay. Once I can show this equation star, right? Then I have gave you what I promised, namely, if you give me a lambda, I can construct an elliptic curve for you, and the C mod lambda is identified, has a bijection to the set of C points, complex points on this elliptic curve I constructed for you. Okay, great. So how do we show this? Okay, so to show this, first of all, let me make a definition, because I want to define some constants A and B associated to a lattice, right? So let me actually define some constants associated to a lattice. So given some lattice inside C, okay, we are going to define the so-called Eisenstein series. Series of weight to k is the series given by, so denoted as capital G, 2k of lambda. So given a lambda is a value. It's a summation of omega in lambda, omega not equal to 0, 1 over omega to the 2k. Okay, so the point is for all k greater or equal to 1, this series is 2k lambda is absolutely convergent. Okay, so very concretely, This means that if you give me a lattice lambda, if you give me an integer k greater than 1, G2k of lambda is just a number. Okay? So it is just a constant associated with a lattice lambda. Okay? It's just a number, nothing complicated. Okay, great. So sometimes when we know what lambda is, we will denote this number by G2k. Okay, so then how is Eisenstein theory related to our functions? Well, if you go back to the definition of my Walsh's P function, you see that, so what we have is the Laurent series. The Laurent series at z equals to 0 for the Walsh's P function is given by 1 over z squared plus sum of k from 1 to infinity 2k plus 1 of g 2k plus 2 of z to the 2k. Okay, great. So, and we can also take the derivative. We can also consider the Laurent series of a derivative, which you can compute, right? Then the point is, then here comes a very important point, is that the only holomorphic elliptic functions are constant functions. Okay, so then by comparing the order of poles at z equals to 0, we can set up an equation between powers of p and the powers of p prime z. So when you eliminate the pole using p and p prime, you get a constant function, and that calculation will tell you exactly that p prime of z. So Walsh's p function derivative satisfies the following equation. So p prime of z squared equals to 4p of z cubed minus 60 G4 P of Z minus 140 G of 6 for all Z in C mod lambda. Okay. Sorry, C, not C mod lambda. For any C away from lambda. Okay, great. So this is what I promised you, right? So then this value is the capital A I was telling you about, and this value is my capital B. So now with this differential equation about the Walsh's P function in hand, I'm able to construct you an elliptic curve E lambda, such that the set of complex points on E lambda are identified on one-to-one bijection to the set of points on C mod lambda. So this is how so let me actually write out the theorem just to recall what I'm saying. Okay, so given a lattice lambda in C, we can define an elliptic curve E over C be the curve defined by y squared equals to 4x cubed. Well, you can also change variable to get rid of this 4 if you want. Minus 60 of the G4 value associated with lambda minus 140 G6 value associated with lambda. Okay, so then it is an elliptic curve. Well, because it's defined by a Walsh's equation. And this map, phi from C mod lambda to E given by Z map to P of Z, P prime of Z, is a complex analytic isomorphism of Lie groups. Is a complex analytic isomorphism of Lie groups. So what does this tell you? So this tells you, first of all, really that if I think about an elliptic curve over C and think about this set of C points, it is given by a torus, right? It's very concretely given by, I have my complex plane and I took a parallelogram and I identified the two parallel sides of a parallelogram. I got a torus, and this is complex analytically isomorphic to my elliptic curve. And moreover, this gives you a way to very concretely see the addition law on elliptic curve. Because if you think about this torus, this C mod lambda, its addition law is inherited from the addition of complex number C. And this is the complex of Lie group. So the addition on the elliptic curve of this set of complex points is exactly agrees with this addition on complex numbers. So this gives you a very concrete way to think about the addition law on elliptic curve over C, the case over C. And moreover, this also gives a way to visualize the set of torsion points for elliptic curve over C, right? Think about where the torsion points are. That's an interesting exercise and very important. Okay, so now we have did half of our goal one. So our goal one was to identify two categories, namely lattices in C up to homosity and elliptic curves up to isomorphism. So now to each lattice in C, I have associated with to you a elliptic curve, right? Now it's time to go backwards. If I give you a complex elliptic curve defined over the complex numbers, now I want to find the corresponding lattice for you. Okay, so next goal is go backwards, namely associate a lattice lambda in C to an elliptic curve. E defined over C. Okay, so how do we do this? Well, so think about it. So what is a lattice? Well, a lattice, as we said, it is nothing but a free rank 2 free Z module in C that are linearly independent, right? A lattice is literally given by something like omega 1Z plus omega 2Z, right? Where omega 1, omega 2 are two complex numbers which are linearly independent. Right? Okay, so great. So this means that if I want to construct a lattice, I only need to give you two complex numbers, essentially. Okay, so now the question becomes, if I have an elliptic curve, how do I construct two complex numbers? How do I pull out two complex numbers out of my elliptic curve? Well, so my elliptic curve E, right? We have a Weierstrass equation. Let's see, it's given by Weierstrass equation. Y squared equals to x cubed plus ax plus b, right? Okay, and topologically, my C point EC is a torus, complex torus. Okay, great. So this is how I'm going to construct two complex numbers by integration. So recall that I have an invariant differential called omega, which is given by dx over y on my associated to my Weierstrass equation, right? Okay, and then if I think, let me use a different color. If I think about my torus, I can also think about its simple closed loops. So this loop, let's call it alpha. And then this loop, let's call it beta. So the point is, my set of, okay. So the point is the loops alpha beta generate the singular homology of my torus. So generate H1 EC Z singular homology, right? So great. So now I'm just going to give you two complex numbers as follows. Omega 1 defined as integrate my omega dx over y along my simple closed loop alpha. And then omega 2 will be I'm going to integrate dx over y along my simple closed loop beta. Okay? This will gives me two complex numbers. And this omega-1 and omega-2 will give me a lattice in C. And they will be linearly independent, as a matter of fact. And moreover, if I instead of choosing this, if I choose a different basis, it will not change my lattice. It will just change the generator of my lattice. It will not change the lattice. Okay, so this actually is a canonical way to associate to a curve over C with a lattice in C. Okay, so the lattice lambda, which we define as omega-1z plus omega-2z. Okay, and we can define the following map. So I want to identify the set of C points of E to C mod lambda. So this would be the inverse map of this map phi we just talked about. Okay, so phi associates every point in C mod lattice to a complex point on E, right? So now I have an elliptic curve and I construct a lattice for you, and I'm going to associate each complex point of my elliptic curve to a point on this quotient, this C mod lambda. How am I going to do this? Well, I will take any point P and map it to the integral from O to P dx over y, where O is the base point of the elliptic curve, or identity point of the elliptic curve. It's O, let me just see the marked point. Okay. This will give me this identification exactly okay, so this map is also a complex analytic isomorphism Lie groups. So complex analytic isomorphism Lie groups. Okay, so this is how we essentially identify isomorphism classes of elliptic curves defined over the complex numbers with lattices lambda inside C up inside the complex plane up to homocity. Okay, great. This is what we want to talk about, which is elliptic curves defined over the complex numbers. So this gives you a concrete way to think about topology of elliptic curve and also think about the group law of elliptic curve. And moreover, as I said, it gives you a very concrete way to see the set of torsion points, like where are the points on the curve which has order 2, right? Okay, so the next topic is we want to think about how to explicitly construct elliptic curve with complex multiplication, right? So this is the topic of our lecture series, and I gave you a definition last time, but I never proved to you that such elliptic curves exist, right? If you think about our proof of the endomorphism ring structure of the curve, it's just we eliminated all other possibilities down to when I have a curve defined over a characteristic zero field, I have only these two possibilities. Either its endomorphism ring is isomorphic to Z, or is slightly bigger than Z, right? But these are eliminated down. So I never proved to you that both cases occur. Right. So, well, since this lecture series is on elliptic curve with complex multiplication, probably this is not an empty set, right? But how do I actually construct an elliptic curve with some desired complex multiplication? This is the topic next. Okay. Okay. So since every elliptic curve over C, I can think it as really constructing a lattice in C. So this means that to construct, so let's start. So to construct an elliptic curve E over C with endomorphism ring bigger than Z, larger than Z. Z is the same as constructing a lattice lambda inside C such that there exists some alpha which is not in Z, and alpha lambda is inside lambda. Because we just talked about morphisms between C mod lambda 1 to C mod lambda 2, right? So now I want to think about endomorphisms. So I want to think about endomorphism of C mod lambda, right? Then they would be given by complex numbers. So I want maps from C mod lambda to C mod lambda. This means I would be given, what I want is complex numbers such that complex numbers alpha such that every point Z gets mapped to alpha times Z over C, and such that alpha of lambda is inside lambda, so it is well defined. So this is actually where the name complex multiplication comes from, where the word multiplication is from. Because if you look at a set of complex numbers of elliptic curve over C, being identified with the points on C mod lambda, when the endomorphism applies on this set of points, it is literally by multiplying the corresponding complex number Z with this complex number alpha that represents your endomorphism. So this is where the name complex multiplication from. Okay, so how do I construct such lattice lambdas? Okay, so first of all, let's recall what kind of lambda we can have. So we kept on saying that the endomorphism ring of elliptic curve over characteristic 0 is either Z or an order of an imaginary quadratic field. But last time I never wrote down a definition of an order of an imaginary quadratic field. So let me start there. So definition, an order O of an imaginary quadratic field K, which where K you can simply write it as Q or Joy squared minus D, imaginary quadratic, is a subring of K such that O is a rank 2 free Z module. So order in an imaginary quadratic field K is nothing but a subring of K, and meanwhile it's also a rank 2 free Z module. So the consequence, so that's first of all, the example is OK, which is a ring of integers. So the ring of integers of an imaginary quadratic field is an order. And moreover, so for any order O in K, you can show that it's not hard to show that it's actually O has to be a subring of OK. So this is why OK is also called the maximal order. So the ring of integers of the imaginary quadratic field is called is the maximal order. Okay, and O is always a finite index subgroup. Okay, finite index subgroup of OK. Okay. So the endomorphism ring of identity curve over C is either Z or isomorphic to one of these orders. Okay, great. So then if you give me an order O, give me imaginary quadratic field K and an order O in K, how am I going to construct an identity curve with exactly endomorphism ring isomorphic to K? Well, the point is, how do I construct the lattice, right? So here's how you do it. So first of all, essentially I want something that when I multiply O to it is, so I want a lattice lambda, right? Such that for any element in O, so I want for any alpha in O, right? I want alpha times lambda inside lambda, right? Then what does this format remind you of? Well, ideals, right? So if I have a ring, and then I want some structure such that for any ring element multiplied to this set is still contained in this set, then I should be looking for something that looks like an ideal. So let me give you the following definition, namely fractional ideal. Okay, fractional ideal. So a fractional ideal of O is a subset of K, which is a non-zero finitely generated O module, okay, which is a non-zero finitely generated O module. Okay, O module. So it is of the form, very concretely, it is of the form alpha times A for some alpha in K star, and A is actually an O ideal. It is an O ideal. So the point is, an O ideal is, well, an ideal is first of all a subset of the ring, right? But a fractional ideal, we don't ask it to be a subset of O. We only ask for it to be a subset of K. So what you do is you take an actual ideal, O ideal, A, and then you are allowed to multiply any non-zero element of K. Then such a structure is called a fractional ideal. It is a subset of the field K. Okay, so a non-zero fractional O ideal is a rank 2 freezing model. Okay. Well, a rank 2 freezing module. What does that remind you of? Namely, a lattice in C. So the point is, you can choose an embedding. Under an embedding, K embeds into C. There are two embeddings because K is imaginary quadratic. The image of a fractional O ideal is a lattice. Is a lattice lambda in C, such that alpha times lambda is in lambda for any alpha in O. Okay? So this means that it corresponds to an elliptic curve. It corresponds to an elliptic curve E over C, such with with O in as a subring of its endomorphism. So this is over C, endomorphism ring. Okay. So currently O is a subring. So for first of all, E definitely, okay, E has CM, right? Because well, O is a subring, right? So then the next question is, when is O actually isomorphic to the endomorphism ring of E? So then the next question is, when is O isomorphic to NCE? Well, the answer is when the fractional ideal is so-called proper. Or another property you can measure it is by invertible. So let me define what it means. Proper actually is literally the definition of what we're claiming here. Proper means that O, so a fractional ideal, let me call it A. A is proper if O literally equals to alpha in K, such that alpha times A is inside A. So this is essentially the definition of O being isomorphic to the endomorphism of lambda, of C mod lambda or EC, right? Another thing is there's another notion called the invertible, which means that there exists fractional ideal, O ideal, B. Okay, fractional O ideal B, such that AB is equals to O. Okay, and then it turns out that proper, proper if and only if invertible. Okay. Okay. So, and also, since as you can see from the definition of proper guarantees that the endomorphism is not bigger than O, right? So this tells you that any fractional ideal of the maximal order is automatically proper. Ideal of the maximal order is proper. Okay, so the point is, if you give me imaginary quadratic field K and the order O in K, and you ask me to construct an elliptic curve E defined over C, whose endomorphism ring is isomorphic to O, then what you need to do is essentially when we can do it. Well, next we're going to prove that it's the only way to do it. Now we just learned that when we do it is to find a proper fractional O ideal and embed your imaginary quadratic field K into C, then under this embedding, the image of this fractional O ideal will be a lattice, and that lattice will correspond to a elliptic curve with the property you desire. Okay, great. So then how many such elliptic curves are there? How many isomorphism classes of elliptic curves satisfy this property that is ring of endomorphism ring is isomorphic to this given O? Well, here it is. So, okay, great. So the point is, how many can we construct this way? Next, we'll prove that all CMP curves arises from fractional ideals. Okay, so how do we counter that? Well, namely, the point is we want to take all proper fractional O ideals, right? But there's some equivalence among them. Namely, when I take all the lattices, I need to model out homosity, right? When I take all the curves, I need to model out isomorphism relation. So for fractional ideals, how do I recognize which ones will give rise to homothetic lattices? Well, this is given by modding out. So first of all, actually I should have said one thing. So the set of proper fractional ideals, because proper fractional ideals are invertible, it turns out that the set of proper fractional ideals forms a group by multiplication, where O is identity element. So it forms a group. Okay, and inside the group we can construct a subgroup, namely, okay, so namely a fractional ideal is called invertible. Sorry, it's called principal if it's of the form, it is of the form alpha times O for some alpha in K star. So in general, a fractional ideal is given by alpha times O ideal, right? But if I take the trivial ideal, if I take the whole ring O and multiply by a non-zero element in K, then it is a fractional ideal, and such a fractional ideal we will call it principal. And the set of principal ideals will form a group. So the set of principal fractional ideals form a subgroup. So, if a fractional ideal is principal, it is always invertible because you can take alpha inverse times O, right? It's also a principal fractional ideal, and then it is literally inverse, okay, of alpha O. So form the subgroup of the set of the ring is a group formed by proper fractional ideals. So I will call this I of O, and the forms a subgroup which we'll call P of O. It is a subgroup of I of O. Okay, so then we can define their quotient by I of O mod P of O. This is called the class group of the order O. And this is a finite group. This is a finite group whose size is called the class number of O. And it actually classifies isomorphism classes of elliptic curves with Cm by O, even though we have not defined it, because we have not proven it, because I have just told you if you give me a fractional ideal under the embedding of into C, I get a lattice which gives rise to an elliptic curve with that Cm, right? I haven't told you the converse statement. Namely, if I have an elliptic curve E over C whose endomorphism ring is isomorphic to O, I should give you a fractional ideal back, so that is a bijection. Okay, so let's actually do that before. That's the last thing we want to do, namely, okay, namely, okay, this is the last thing I want to do. So to prove the following theorem, which is a lattice lambda has Cm. By that, I just means that, well, that means C mod lambda, I guess, has Cm, or the curve has Cm, whatever, right? If and only if lambda is homothetic to a lattice of a proper fractional ideal of an order O of an imaginary quadratic field K. So then if I prove this theorem, this will tell me that all elliptic curves with Cm by O, excuse me, arises from a proper fractional O ideal, right? And also the homosity of the lattices are exactly measured by whether the two lattices are differ, by whether the two fractional ideals differ by a principal friction in the deal. Then this will tell me that the class group exactly parametrizes isomorphism classes of elliptic curves over C with Cm by O. So after I prove this theorem, then we very explicitly know the set of Cm elliptic curves with Cm by a specific order, right? We can very concretely construct it, and also we know how many there are. Namely, we can compute this class number, right? For example, you can use magma to compute this class number. Okay, great. So we will finish this lecture by prove this theorem. Okay, so one way is very clear, namely, if my lambda, so this direction is already proven, already done, because if lambda is homothetic to a lattice of proper fractional ideal of order O, then it has Cm, right? So we only need to do this direction, namely, if I have a lattice lambda having Cm. So what does that mean? That means there exists some alpha inside the endomorphism of lambda, right? So the point is we have that alpha lambda inside lambda, right? Okay, so first of all, we recognize that, well, lambda is given by some omega. So lambda is generated by two elements, omega 1 and omega 2. Right? Then up to homosity, I can divide out omega 1. I can, up to homosity, we can have lambda simply given by take omega 1 equal to 1, or in other words, I can divide out omega 1 up to homosity. We can take, okay? So lambda can be given by z plus, I will just use the other generator called tau, z plus tau z for some tau. C not in, right? Okay, great. Okay, so now this means that, okay, alpha times lambda inside lambda, right? So this means alpha times 1 is inside lambda, means alpha times 1 equals to a plus b tau for some ab in z. And moreover, alpha times tau need to equal to c plus d tau for some cd in z, right? Because alpha times lambda inside lambda by assumption. So then this implies that you get the following equation: a plus b tau, which equals to lambda, times tau equals to c plus d tau, okay, which is a quadratic equation in tau. Okay. So since one tau generates a lattice, we know that tau is not real. So essentially, the field we are looking for, the imaginary quadratic field K, we are looking for is Q adjoint tau. And then the order O is exactly beta in K, such that it's an endomorphism. And it will be an order of K where, so this is the order of K, where lambda is a proper OID, O fractional ID. So this is if I give you a lambda or give you a elliptic curve over C with Cm, how to find the imaginary quadratic field and its corresponding order. Okay, that's all I want to talk about. Thanks for listening. Bye.